Hi, everyone, and welcome to this episode of Foundry Fireside. My name is Brandon Trin, and I'm an intern on the Foundry communications team. Today, I'll be chatting with one of the Foundry's postdoctoral researcher, Anika Promi. Welcome, Anika. Could you please introduce yourself?
Thank you, Brandon. I am Anika Promi. I am a postdoctoral researcher at the Molecular Foundry at the Berkeley National Lab. I did my PhD at Virginia Tech in chemistry, where my work mostly focused on understanding the synthesis of lithium and sodium-ion batteries. And now my work sits more on the intersection of material science, chemistry, and AI for science. Broadly, I'm looking at how we can use data from past synthesis literature, current experiments, and characterization results to make better workflows for making functional materials, especially complex oxides, and also how to do this using large language models. Mostly, I'm interested in making material science and material discovery more systematic, data-driven, and easier to learn from the vast unstructured data.
Thank you for sharing, Anika, and for taking the time to chat with me today. How about we get started with you telling us a little bit more about yourself? What led you to become a material science researcher?
I think what led me to become a material science researcher is the fact that I have always been driven by discovering new things. And I feel like material science is a field that gives me that feeling constantly. For example, if I talk about my work of synthesis of complex oxides, this is something where you can make small changes in the synthesis process, and then you can see completely new reaction pathways, material properties, and new material behavior. And I feel like that is something that really excites me as a scientist, and I find that really fascinating. And I also like the fact that material science sort of sits in the intersection of chemistry, physics, engineering, and now also data science and AI. And there is always something new to learn. And I feel like that combination of curiosity and problem solving is sort of led me here.
I'd love to go back a bit further. When you were in high school, did you imagine yourself becoming a material science researcher, or did you have a different career in mind?
I don't think I had the full picture of becoming a material scientist when I was in high school, but I think I was always very interested in chemistry. And I was doing well in chemistry as well. And then I did my undergrad in chemical engineering, which sort of gave me this process-oriented way of thinking about things, synthesis, just, not uh, teaching me not what a material is, but also how to make it, how to scale it, and that sort of thing, basically how to have more control over how you make a material. And then I did my PhD in chemistry, where I became more deeply involved in both chemistry and engineering, working with battery materials, especially gaining more experience in material synthesis and characterization. So from there, I think material science sort of became like a very natural space for me. And I feel like that it combines very fundamental chemistry with all the process-oriented thinking and also like very real world application of things. So yeah, that's sort of like where I am right now. And not exactly the whole picture in high school, but yeah.
Thank you so much for sharing your journey with me. I think as a high schooler right now, that is something that I could learn from. Going back to today, your current work focuses on creating AI learnable synthesis workflows. What's that mean in practice?
I think in practice, it means making material science both and synthesis understandable to both humans and AI. A lot of synthesis data that exist in literature, like in published literature, experimental records, and also there is a lot of researcher intuition involved, but it is not always organized in a way that is easier to reason across or compare from. So my work starts from synthesis databases and using large language models. I try to reason across many different reported recipes rather than looking at each recipe one by one. I'm also interested in how these models respond to different kinds of prompt architectures. For example, how the quality of the hypothesis that they generate about synthesis can vary depending on the amount of data and context that you provide. And so the overall goal is to identify patterns, generate hypotheses, and ask questions like, which synthesis parameters control the phase formation, what conditions lead to impurities, and what strategies might transfer from one material system to the other. And then I sort of take these hypotheses generated by these large language models and then take that insights back to experiments. I use sol-gel synthesis to test specific synthesis variables, and then using synchrotron X-ray based characterizations, I try to find the mechanistic reason behind why a particular variable affects the phase composition in a certain way. And while doing this, negative data is also important, right? When a particular synthesis doesn't work the way your hypothesis suggested that it might, it's also important to look at why that hypothesis failed, because that can sometimes be more informative than positive results, right? So the bigger idea is to move from isolated trial and error and toward the more guided and data-driven way of discovering materials and making those materials. And the goal is not to replace the scientists, but also to give the scientists better tools so that they now have a better map of the synthesis space of the material that they're working with.
As a follow up to my previous question, what do you think are some limitations of AI in scientific research?
I think some of the limitations of AI is that, AI is only as good as the data and context you provide. And as I said, like in scientific literature, data can often be incomplete or inconsistent or sort of biased towards positive outcomes, right? For example, if I am making 10 attempts at making a material, maybe 2 of those attempts were successful or gave me outcomes that I really wanted. But oftentimes only those 2 attempts would get reported and not all the failed attempts at making that material. But that information is also important because that tells you where like the boundaries are, right, in the synthesis space. And so the unstructured nature or the incomplete nature or the lack of negative data in synthesis can be a limit on how much AI can do for us in that space. AI is like really good at identifying pattern, but then it also does not automatically understand like mechanisms a way that a scientist does with their maybe intuition that they generated through years of training, right? So in a way, I think AI can be like a complementary tool that scientists use. And there's also the need for trust and verification. Like it can help you navigate a large amount of data in a much shorter time now, right? And it can like empower you with new tools that would otherwise take you very long time to design and to achieve things. So now I think it's like an empowering tool to scientists where they can like do a huge amount of work in a much shorter time. But I don't think it replaces the need for experimental validation that a scientist provides. Like it can give you very reasonable answers, but you still need to verify those, like with your experiments and sort of like uh, help AI understand the mechanism behind its reasoning. And so I think overall, maybe the future of AI is not really to replace scientists, but to work with them so that they can navigate larger spaces and find patterns faster. But I think human researchers still need to provide the scientific reasoning, the skepticism, and experimental judgment.
I know you've also done extensive work on lithium batteries. Could you tell us a bit more about that and how you think battery technology will evolve to support large scale uses like electric vehicles?
Yes, so I did my PhD on sodium-ion batteries. So I think in many applications, we are using commercial lithium-ion batteries, but what sodium-ion batteries enable us is to use much more earth-abundant minerals to make those batteries and sort of help us overcome the supply chain constraint that we have for many critical minerals, right? But then when you try to incorporate new elements in a material, it sort of brings its own sets of challenges in synthesis. So my work sort of focused on that how we can control different synthesis conditions to incorporate many different transition metals, many diverse transition metals in a battery material, and how to make a better material and how synthesis conditions sort of affect their structure and performance. And for and how this space is evolving for applications like electric vehicles, I think it's like evolving very fast. And this is so battery materials can be like really complicated, and there are many interconnected variables that affect their both structure and performance. So it's not like I don't think the idea is sort of like trying to find the perfect material, but uh, making advancement in many different dimensions. For example, we might want a longer cycle life, but we also want higher energy density. We want higher safety, lower cost. So there are many different dimensions to a battery chemistry. And I think the space is evolving very fast. There are exciting new discoveries in solid state battery and sodium ion batteries. But for the future, I think we need a sort of concerted improvement in both like achieving better material design, better manufacturing control, smarter diagnostics, and also efforts in recycling materials as well.
Thank you for sharing that. And now to bring a few more ideas together, do you think your current work on AI workflows could be deployed to accelerate the battery work you used to do? And if so, how?
Yes, definitely, because I think battery materials are a perfect example where these AI learnable workflows can be very useful because there are so many interconnected variables in the entire pipeline of starting from making the battery materials to make the actual batteries and then testing their performance and cycle life and things like that, right? So, for example, there is the composition of the material. There is precursor chemistry, synthesis temperature, atmosphere, particle morphology, coating, doping, and electrochemical cycling conditions. And all of these can influence the final performance of the battery materials, right? So, for example, in my earlier battery work, central question to my PhD thesis was that while we make a cathode material, we have 7 to 8 different reaction parameters that we could be controlling, right? And so it would take me a very long time to really understand how each synthesis variables affects the final material quality. And I think these are the sort of spaces where we have a lot of already like data available in the literature. And it is a perfect space where an AI can learn and reason across the existing literature to help me identify what are the highest value parameters that I should be tuning first that can have the most impact on improving the phase purity of my material. And there are many other examples like this in the entire battery literature space where you could be employing AI-driven workflows to better inform your research work. And that's why I think my current work is very transferable to battery materials as well. I think the material system can change, but the core challenge and the core idea is similar, that how do we understand a large synthesis space and make better decisions with less trial and error and with more high value experiments that the large language models can help us identify. So, yeah.
Thank you so much for sharing that. And what is one upcoming project you're excited about?
One upcoming project that I will be working on is my work focuses on sol gel synthesis for complex oxide materials. And in literature, we can see that there are many different classes of sol gel reactions. So you could choose to make one material through maybe like a metal complex reaction pathway, or you could choose a polymerizable reaction pathway, or you could do a colloidal reaction pathway. So there are many different ways you can make one material, and obviously how you choose to do that affects the quality of the material that you're making. But again, we have these thousands of sol gel recipes on different complex oxide materials, but they're not structured. And as a human, you can only read so many papers and you can only process so many recipes in your head, right? So my work would be to design an agent that can, so like an AI agent that can take all of these recipes, classify them according to different sol gel recipe types, and sort of like give us a big picture on what reaction classes lead to higher phase purity of the material versus what are the parameters in your reaction that mostly lead to impure material, which can then, lead to maybe a detrimental performance of those material in their application. So I will be taking almost more than 100,000 reactions and sort of like working with that agentic AI, classifying them into different classes, and then see how they affect the quality of these material, and sort of make better decisions on what we can change, what small things we can change that can help us bypass this problems in material synthesis.
That sounds very interesting. I look forward to hearing more about it. Now, if you could go back in time to meet your, let's say, 16-year-old self, what advice would you give yourself?
I think I would tell her to be less afraid to step out of her comfort zone. And I would tell her that many amazing things happen when you do that. And also to stay curious. And then it's okay to not have everything figured out at a young age. And then you'll always figure things out along the way. Uh, and yeah, so be like brave and always step out of your comfort zone and discover new things.
That's all the questions I have today. Thank you so much, Anika, for taking the time out of your busy schedule to talk with me today. It was really great to learn more about your research. And for those of you watching, if you're interested in learning more about research at the Molecular Foundry, stay tuned for more episodes of Foundry Fireside.